Okay, so let's go back to what we learnt in the very first lecture in this section of the course. So think of a VPC as a logical data center within AWS. You can have VPCs in every region in which AWS exists. VPCs can span multiple availability zones, but what VPCs can't do is span multiple regions. So you always have a VPC in a predefined region. VPCs consist of internet gateways or virtual private gateways. If you're doing like a hybrid cloud and you're using a VPN to connect into your VPC, they consist of route tables, network access control lists, subnets, as well as security groups. One subnet always equals one availability zone. I cannot stress this enough. It comes up all the time. Just remember that and you'll be fine. You cannot span a subnet across multiple availability zones. Security groups are stateful. Network access control lists are stateless. And all we mean by that is when we open up port 80 in a security group, both the inbound and outbound rules automatically allow port 80, whereas if with network access control lists, we have to go in and do allow or deny on both our inbound and outbound rules. You can peer VPCs in both the same account and with other AWS accounts. So you can have a VPC peering arrangement with a completely separate AWS account. That does definitely work. But remember, there's no such thing as transitive peering. What do we mean by transitive peering? Well, typically this is called a hub and spoke design. And this is where with VPC A, we would have all our central servers. So we'd have things like our Active Directory servers. We'd have our servers that do all our monitoring. We'd have our antivirus servers. And then they would then peer with different VPCs. So VPC B might be our production environment. VPC C might be our testing environment. VPC D might be our developer one environment. VPC-E might be a second developer environment. And basically, if they need to access Active Directory, or if you've got antivirus agents installed on all the servers in these VPCs, they're going to need to peer back to VPC-A. But if we have VPC-B and we want it to talk to VPC-C, it cannot do that through VPC-A. There's no transitive peering. Instead, we have to allow a direct peering connection from VPC-B to VPC-C. Moving on to NAT instances. When creating a NAT instance, always remember to disable source and destination checks on the instance. NAT instances have been around for as long as I can remember, whereas NAT gateways are very, very, very new. But NAT instances do come up in all the associate exams. So you do have to really know NAT instances inside out, even though really they should start going away now. NAT instances must be in a public subnet, and they must have an elastic IP address assigned to them to work, and there must be a route out of the private subnet to the NAT instance in order for a NAT instance to be able to work. And the amount of traffic that NAT instances supports depends on the instance size. So if you're bottlenecking, if you're using a T2 micro, for example, and you've got huge amounts of outbound traffic to the internet or inbound traffic from the internet, you're going to need to increase that instance size. And you can create highly available or high availability using auto-scaling groups, multiple subnets in different availability zones, and scripts to automate failover. So it is definitely possible to have a highly available NAT instance, but it's also a pain to set up. And NAT instances are always behind a security group. Now, NAT gateways are not necessarily in the exams just yet because they are very new, but it's still good to know about them because you're probably going to use them in the real world. You'd always use a NAT gateway over a NAT instance, in my opinion. I'm sure someone's going to find a scenario where you wouldn't do that, but anyway, in most cases you would. And they're preferred by the corporate or by the enterprise market. They scale automatically up to 10 gigabits per second. There's no need to patch NAT gateways. AWS look after them for you, whereas with a NAT instance, you've got to run your yum update all the time to keep them patched. And they're not associated with security groups. They're automatically assigned a public IP address. And when you deploy your NAT gateway, remember, just as what you do with your NAT instance, you've just got to add a route out via your NAT gateway in order for it to work. But there's no need to disable source destination checks on a NAT gateway. Moving on to our network ACLs. So your VPC automatically comes with the default network ACL as well as a route table when you first create it. And by default, it always allows all inbound and outbound traffic. Then you can go on and create custom network access control lists, but by default, each custom network ACL denies all inbound and outbound traffic. So when you provision it, it's deny everything, and then you go in and add your rules, and that's a useful security feature. Each subnet in your VPC must be associated with a network access control list, just as it will must be associated with a route. If you don't explicitly associate a subnet with a network access control list, then the subnet is automatically associated with the default network ACL. And again, if you don't, if you don't associate it to a route table, it's going to use your main route table as well. You can associate a network ACL with multiple subnets. However, a subnet can be associated with only one network ACL at a time. And when you associate a network ACL with a subnet, then the previous association is removed. It's really critical to remember that, especially when you're going into the professional levels exams. So just remember, and we saw it happen in the console, if you remember, as soon as we associated our subnet, it deassociated from our main or default network ACL, and then it was associated with the new network or the custom network ACL that we created in the labs. A network ACL always contains a numbered list of rules that is evaluated in order, starting with the lowest numbered rule first. So you remember, if we wanted to deny a specific IP address, we would do a deny first, and then we would allow our HTTP traffic for all other IP addresses. It didn't work when we had our deny in front of our allow. It didn't work when we had rule number 100 and then 101 was our deny rule. We wanted to make our deny rule number 99. A network ACL has separate inbound and outbound rules, and each rule can either allow or deny traffic, and that basically means that network ACLs are stateless. Responses to allow inbound traffic are subject to rules for outbound traffic and vice versa. And then finally, if we want to block IP addresses, we're always going to use a network ACL. We're not going to use security groups because there's no option to deny traffic in a security group anyway. Moving on to NATs versus bastions. So a NAT is used to provide internet traffic to EC2 instances which are in our private subnets, whereas a bastion is used to securely administer EC2 instances. So for Linux, you'd use SSH. For Windows, you'd use RDP. And then you use that bastion to go in and secure your EC2 instances in your private subnets. And so in Australia, we call them jump boxes. I like to remind people of that simply because a lot of Australians will go in and do the AWS exams and think, what the hell is a bastion host? And the other reason is it gives you a very good visual aid in that you basically SSH into a EC2 instance that's in your public subnet, and then you jump across into the private network using SSH, and that's why we call them jump boxes. So basically you're using your bastion host as a way to jump into the rest of your private network. Moving on to resilient architecture. So basically, if you want resiliency, you're always going to have two public subnets and two private subnets. That's because one subnet always equals one availability zone, and you want to spread these across different availability zones. You've got to make sure each subnet is in different availability zones. With elastic load balancers, you need to make sure that they are in two public subnets and in two different availability zones in order to ensure resiliency. With bastion hosts, you should put them in an auto-scaling group with a minimum size of 2, and then use Route 53, and you can either use round robin or a health check to automatically fail over between your bastion hosts, and that will protect you against an individual virtual machine failure as well as an entire availability zone failing on you. And then NAT instances are a little bit trickier to make resilient. You need one in a public, you need two, one in each public subnet and each with their own public IP addresses, and then you need to write a script to fail over between the two. Instead, where possible in real life, you just want to use NAT gateways and then Amazon handle the failover for you. And then finally, you can monitor what goes on inside your VPCs using VPC flow logs. So that is it for this section of the course, guys. If you do the SA Associate exam first, do remember that you've got a very small delta in terms terms of study to pass the developer and the SysOps administrator associate. There is a lot of common ground between all three associate exams, and if you know this networking section inside out, you're so well prepared to not just pass the SA associate, but to pass the other two as well. So if you have any questions, please let me know. If not, feel free to move on to the next section of the course. Thank you.